the cycle of Krebs. First, we are going to transform the circle into a square where we have 4 clear positions, 4 corners and 4 middles. First compound is citrate, first found in lemons and taking their name from it. First corner, citric acid or citrate. A very similar compound comes next, isocitrate. Only a small difference between these 2 molecules. Then comes a more complicated name, alpha ketyl glutarate. Is keto, no kettle, but it will remind us of the name, alpha ketoglutarate. Next, we have succinyl coenzyme A. Coenzyme A is a very large, stable molecule, here represented with a catapult. This is the active point where an S, a sulfur atom, links to the active part of the compound. This is an octopus full of suckers at the back. Succinyl coenzyme A. Next compound has more suckers. Is another octopus. This time is not succinyl coenzyme A, is succinate in the lower corner. The next position is for fumarate, fumes, the root for smoke and smoking from a pipe, fumarate. Final top corner is malate, malate, although everybody says eating apples is good for you. So I have an apple, Latin root, malate, with a mallet at the top, malate. And the final spot is for the oxaloacetate. This is an ox, a bull with no balls, and this is acetate, the material most commonly used for glasses. Oxaloacetate. 8 compounds around the cycle of Krebs. Now we are going to see what is coming in and out of this cycle. And there are 3 things that we are going to look at. CO2, water, and energy. And to find that out, we need to know what are the number of carbons in each of these compounds. The vertical right-hand side has the most carbons. 6 each lemon, citrate and isocitrate. 5 for alpha ketoglutarate, and everybody else will have 4 carbons. So it's easy to see where are the 2 carbons lost, or the 2 CO2, between isocitrate and alpha ketoglutarate, and 5 to 4 between alpha ketoglutarate and succinyl coenzyme A. So we can envisage our kettle boiling and producing 2 molecules of CO2 who land 1 to each side. Here and here we have 2 CO2 coming out of the cycle. Now water. the water is a bit more spread out on the circle, and there are 3 places. There is a molecule of water coming here and a molecule of water coming out again in an intermediate compound. There is a molecule of water that comes in between the fumarate and the malate. We can almost see the pipe getting a little bit of water inside and chucking it on top of the apple. And the final molecule of water is in here, between the oxaloacetate and the citrate. Of course, we are missing 2 extra carbons here for the cycle to continue. Those are coming from acetyl-CoA, which is not represented here. But you can see our oxaloacetate spitting on top of the lemon a molecule of water. And now we are going to see what we do with the energy. All this energy is produced in each turn of the cycle. The easier one to see first is the smaller one. This is a GTP. It's roughly equivalent to an ATP. And it comes between the 2 octopus. We can almost see the succinyl coenzyme A passing on the battery to the succinate. This is where the first of the energy production is located. The next one is this one. FADH is a slightly larger production. It's equivalent roughly to 2 ATPs. And it will come in here between the succinate and the fumarate. And again, it's not difficult to see the octopus giving the pipe a battery. It stays there. The next 3 are going to be located into the areas where no water is involved. Batteries and water don't go very well together. They are slightly larger, and they are equivalent roughly to 3 ATPs. So we are going to locate them in the areas left with no water or no battery. One is here, between malate and oxaloacetate. Water, water, batteries, water. The only 2 places are this, with the 2 CO2 at both sides of the alpha ketoglutarate. So if we add up all the energy produced in one turn of the circle, we have 3, 3, 6, 7, 8, 9, 10, 11, 12. 12 ATP roughly produced in one turn of the cycle.